any homework questions you want me to go over? Yeah.
Number 8.
On Newton's laws. This one? Okay. All right, so we got these two masses connected to each other by a cable that passes through this pulley. And we want to calculate the acceleration of the 1 kilogram mass, and then the force vector the cable applies to the two. So this is one of those cases where you have two connected bodies, but their accelerations are not going to be the same, because if one's going up, the other one's going down. And so what we're going to do is choose one of these two to analyze first, come up with equations from Newton's second law, then go to the other one, and then, eventually we'll solve the system of equations. It doesn't matter which one you choose first. I guess I usually go choose the one farthest on the left first, but I think I'm actually going to choose the one on the right first this time so you can see how the signs kind of work out. So free body diagram of body 2, the 2 kilogram body. There's a weight force down of 19.62. There's a cable force up of T. And since this is the first body, all we have to figure out for the acceleration is this thing moving along the x-axis or the y-axis? This is going up or down, so it's the y-axis. So I'm going to represent my acceleration vector as just 0a. And the reason I wanted to do the 2 kilogram one first is to point out that, you can look at this and see that the 2 kilogram is going to accelerate down and the 1 kilogram is going to accelerate up just because of their different weights. But you don't have to recognize that. All you have to do on that first body is determine, is it along x or along y? Okay, so now we'll go to Newton's second law. We have 0, negative 19.62 plus 0t. Those are the only two forces, and this is equal to the mass times what we decided to call the acceleration, 0a. And we get two equations from Newton's second law. The x equation says 0 equals 0, which obviously isn't of any use, The y equation is the one that we're going to come back to. This is the one that says negative 19.62 plus t is equal to 2a. Okay, and this one's going to be useful because we're trying to calculate stuff related to the acceleration for part A and related to the cable tension for part B. And both that A and that T that we need for those are in that y equation. Okay. Well, so I'm just going to set this aside and we'll come back to it. We can't solve it yet because it's one equation with two variables. And so now I'll go to the free body diagram of the 1 kilogram. This has a weight force down of 9.81. Hi.
Can I grab a copy of the test? Is there a quiz?
Oh, there is a quiz, yeah. Thank you. Sorry about that.
No problem. Are they allowed to use a calculator?
They don't need one. It won't help, but
Good, thank you.
they can use it as an emotional support device. Okay, so there's a free body diagram of the second one. But now on the second one, you do have to think a little bit about the acceleration. And the way you do it is you think, okay, if the first body I chose moves an inch in its positive direction, where does this second body go? Okay, so if this first one moves, the 2 kilogram here, moves an inch in the positive y direction, even though that's not the direction it's going to go, but that doesn't matter. We're just thinking if it moves an inch in its positive direction, where will the second body go? An inch down. Since it's an inch for both of them, the magnitudes of the accelerations are going to be the same. So all we have to think about is the directions. And so if the 2 goes an inch up, this one goes an inch down. And so I'm going to represent the acceleration of this one as 0, negative a. Okay, anybody have any questions about that? That's the trickiest part of doing these problems, is just thinking, okay, I've already decided what I'm going to call the acceleration of the first one. Compared to that, what am I going to call the acceleration of the second one? Okay, so Newton's second law says 0, negative 9.81 plus 0t is equal to the mass times the acceleration. The x equation here says 0 equals 0. The y equation here says negative 9.81 plus t is equal to negative a. And so now these 2 circled equations are my system of equations. So I'm just going to use one to substitute it into the second one. And it doesn't matter which one you substitute into which. I'm going to rewrite this one as t is equal to 2a plus 19.62. So I'll put it in here. We have negative 9.81 plus, from this first one, all this stuff that t is equal to. And that's equal to negative a. And so I get 3a is equal to negative 9.81. And so a is equal to negative 3.27. Any questions about that? So notice how the signs worked out. I chose the one that I knew from looking at it was going to be accelerating down first. I represented its acceleration as 0a, but then the negative value for the acceleration ended up making the signs work out on its own. Okay. So we're looking for the acceleration of the 1 kilogram mass. That's this one. So I'm going to plug negative 3.27 in for a here. And we get that the acceleration vector of 1 is equal to 0, negative of whatever a is. Or in other words, 0, positive 3.27. Or you can think of that as in the positive direction, 3.27. Any questions about that? And then the second part of the question asks for the force that's applied to the 2 kilogram mass by the cable. Okay. Well, if we go to the free body diagram in Newton's second law for the 2 kilogram mass, this is the force we're looking for. We just have to figure out what that T is. And we can get that from these equations. As long as you haven't made any math mistakes, every equation you have up here is valid. So you can just go to whatever one makes it easiest to calculate T. I guess I'll go to this circled one right here just because it's the one right in front of my eyes. So I'll go negative 9.81 plus T, which now we know is negative 3.27. No, T is what we're trying to find. Sorry. Negative 9.81 plus T is equal to negative of what we calculated for A. And so T is equal to 13. No, not quite. Oh yeah, 13.08, I think. Okay. And so now that we have T, we can plug that into this force vector that I circled in green. This is the force onto by the cable. And so the force onto by the cable is 13.08. Or in other words, 13.08 newtons up. Any questions about that? Okay, I want to do one example of these problems where we have a body that's rolling or sliding on an incline. So let's say we have an incline of 10 degrees. And a pulley. And let's say that this has a mass of 4 kilograms. And this has a mass of 1 kilogram. And let's say we want to calculate the acceleration vector of the 4, let's say. And then second, we want to calculate the tension in the cable. Okay. And for something like this, remember when you have rolling and sliding problems on an incline, you always use that rotated coordinate system, right? But when you're doing a hanging mass like this, you don't use a rotating coordinate system. So what do you do when you have one of each of these in the same problem? The answer is you use different coordinate systems for each body. So we're going to use this rotated coordinate system for the rolling cart. And then we're going to use this usual coordinate system for the hanging thing. Yes?
Yeah, so that's what I was wondering with some of the homework, how, like, so when we know to do the rotated coordinate system, it's when it's on an angle. That's when we use that.
Right. Yep. That's right. Only when it's on an angle. Okay, and I'm going to start by isolating the rolling cart. So the 4 kilogram thing. We have a weight force of 4 times 9.81, so that's 39.24. Then we have the cable force. And then we have the pushing force from the surface. Everything here is easy to represent in that rotated coordinate system except the weight. So now we have to think about the weight force vector. So it has a magnitude of 39.24, and this angle here is 10 degrees. So what's the angle all the way from the positive x-axis counterclockwise to the vector? 260, exactly. So the weight force vector is going to be 39.24 times the cosine of 260, 39.24 times the sine of 260. And you get negative 6.81, negative 38.64. And I always think it's worth looking back at it and seeing if the signs make sense. We have two negative components. Does that make sense with where that vector lies? Yeah, because you can see it's in the third quadrant, so both components should be negative. And now, what can we say about the acceleration? Is this thing accelerating along its x or y axis? Is it free to move along its x or y axis? X, yep. That's always true for rolling and sliding problems, so this we're just going to call A 0. So once we know this variable A, then we know the full acceleration vector. So now Newton's second law says negative 6.81, negative 38.64, plus 0n plus t0 is equal to the mass times the acceleration and I can write this in two separate equations. Negative 6.81 plus t is equal to 4a. And the y equation says negative 38.64 plus n is equal to 0. We can't solve these, so we're just going to have to come back to them after we do the other body. Any questions about that first body? Okay, now we're going to the hanging mass. This has a weight of 9.81 and a force from the cable that's away from the body. It's the same cable as in the last one, so I'm going to call this the same thing, T. And we don't have to do any coordinate system stuff with this one. Remember, for this one, we're using the regular coordinate system. But the one thing we do have to figure out is the direction of the acceleration, how to represent the acceleration vector. So, okay, if the 4 kilogram goes an inch in its positive direction, where does the 1 kilogram go? Down. Yep, it goes 1 inch down. Any questions about that? You see that? And so we're going to call this acceleration vector for this one 0, negative a.
it always be like that when there's a cable involved?
Will it always be negative?
Yeah.
No, actually, so if I had done the mirror image of this, let me draw it up here. You don't have to put this in your notes, but if I had done the problem like this, okay, and so say I made this the first body, and then I said, okay, so if this moves an inch in its positive direction, which is that way, where does this one go? This one would go up in that configuration. So you would call this 0A. So you have to do it for each case individually. Okay. All right, so now Newton's second law. 0, negative 9.81 plus 0t is equal to the mass times the acceleration the x equation obviously doesn't help, 0 equals 0. The y equation says negative 9.81 plus t is equal to negative a. Okay, what we're looking for, I mean, like pretty much always with questions like this, is we're looking for an acceleration and something about the cable tension. So we just, the only equations we need to use for that are the ones that have a and t in them. So I'm going to use the first one of these and the circled one here. Okay, so the first one, I'll rearrange this as t is equal to 4a plus 6.81. And I'll substitute that into the second one, negative 9.81 plus the quantity 4a plus 6.81 is equal to negative a. So 5a is equal to 3. And so a is equal to 0.6 repeating. 2/3. That's not 2/3. 0.6 not repeating. 3/5 is 0.6, yeah. Any questions about that? So now that we have that A, now we can look back. We're supposed to calculate the acceleration vector of the rolling thing. Well, here's the acceleration vector. Now we just have to substitute that A into it. So the acceleration vector of the 4 is equal to 0.60. Or in other words, it's accelerating up the ramp at 0.6. If I had made this ramp steeper, you know, if I'd made it 30 degrees, it would be accelerating the other direction, but you would do the calculations exactly the same. It's just that in the end, you would get an A value that was negative. And now we want to calculate that T. You can get that from any equation. I'm going to use this circled equation here. So negative 9.81 plus T is equal to negative of 0.6. And so T is equal to positive 9.75 newtons. Any questions about that? Okay. So now I want to talk about Newton's third law, and I want to talk about it as the third common misconception in this class. Okay, so this is the third thing that we've seen in this class where your intuition is probably a little backwards, and so we have to make kind of an effort to correct it. Okay, so let's think about what the first two were. Common misconception number one. Who remembers what that is?
Objects that are heavier fall faster.
That's right. Yep. So the misconception is heavier objects fall faster. Well, they might fall faster, but so I'm going to say due to gravity. So actually, gravity tries to make everything fall the same. The actual situation is gravity makes anything in free fall accelerate down at 9.81 meters per second squared. And any deviation from that comes from air resistance effects. So what was the video that we watched about that one?
The something tank.
The bowling ball and the feather, yeah, right. They sucked all the air out of the thing and dropped the two. And then common misconception number two. Does anyone remember what that one was?
The bullet.
The bullet, yep. And so the misconception there that a lot of people have is that things moving horizontally are less affected by gravity. And so people have an idea that if you fire a bullet, it sort of, it really just goes straight horizontally until it slows down enough to start to fall. But that's not how it works. It's really falling the whole time. You just don't really see it falling because it's out of your line of sight so quickly. You know, it hasn't fallen very far by that point. So the actual situation is that gravity pulls on any object the same no matter what the object is doing. So whether it's sitting on a table or flying straight up into the air, flying down, or flying horizontally, the force that gravity applies is always the same. Okay, so common misconception number three. So it's often believed that in a collision between two objects, there's a winner and a loser, And the winner applies a bigger force to the loser than vice versa. Okay, so imagine that you have a collision between a semi-truck and a golf cart, you know? There's a pretty obvious winner and loser in that collision. And so people tend to think like, so the force that the truck applies to the golf cart must be much bigger than the force the golf cart applies to the truck. The truth is, those two forces are exactly the same, just in the opposite direction. So say that that collision creates a force, a contact force of 10,000 newtons. The semi-truck applies a 10,000 Newton force to the golf cart, and the golf cart applies a 10,000 Newton force to the truck. That seems weird. It's kind of hard to imagine that. I mean, like if I, hit this paper, the paper looks like it's a lot more affected than my hand is. So you think like, oh, I must have applied a bigger force to that than it applied to me. No, what really happens is those force magnitudes are the same. It's just that this paper is more affected by whatever that force was than my hand is. And similarly, the golf cart is more affected by a 10,000 Newton force than the semi-truck is. Okay, so the actual way it works is at any instant, the two objects are in contact. The force that one applies to two is the same magnitude and opposite direction of the force that two applies to one. There are never any counterexamples to this. It's never a single instant where they're different and then they become more similar or anything. This is always true. Okay. This is called Newton's third law. And the way you've probably heard it before is sort of a paraphrase of the way it's written in Newton's original manuscript, that for every action, there's an equal and opposite reaction. So that's probably the phrase that you've heard before, but that's not a very easy wording of it to work with mathematically. This is, I think, just a better, more concise way to think about it. So mathematically, think of it this way. If bodies A and B are in contact, then the force vector on A by B is equal to negative force on B by A. Okay, so this one isn't very helpful. Think about it this way. So let's think about a couple of cases where this sort of winner and loser collision idea seem very natural, and it's hard to wrap your head around how this works, okay? So think of a baseball being hit by a bat. Okay, so I didn't leave enough room to draw this guy's head, but he has a head, imagine. And so the bat is swinging around this way. And it hits this ball. Okay. So in this case, if you're watching like a pro baseball game, I mean, that ball is going to go flying. The bat and the player are not going to go flying. So it's hard to convince yourself. So what I'm saying is, say that bat for this short duration applies a force of 10,000 newtons to this ball. Okay. The ball also applies a force of 10,000 newtons to the bat. Okay. But why is it that the outcome is always pretty similar? You never see like, oh, that was a bad one, and on this one instead the ball stayed where it was and the batter went flying, Like that seems like that sort of feels like that's what this would be saying, Like there's an equal chance of each one of them to go flying. But remember that they have very different masses. Okay, the bat is attached to a 200-pound person who's also happens to be like wearing cleated shoes and standing on the dirt, And the ball weighs like 0.1 kilograms or something, And so if you apply 10,000 newtons of force to something with a mass of 0.1 kilograms, it has a huge acceleration. If you apply 10,000 newtons of force to something that has an effective mass of, let's say, 400 pounds, based on the grip of the shoes into the ground and the mass and everything, that person isn't going to go anywhere. Okay, so that's the thing. Like you always have to think about the masses of these two objects. Okay, the masses are really what determines which one is the winner and which one is the loser, not the force that they apply. And one thing, if you, I don't know how many of you have ever watched like this probably doesn't even make sense to you anymore, but it used to be, like when I played baseball as a kid, a lot of people used wooden bats, some people used aluminum bats. And so sometimes bats would break, the ball hits it wrong and it breaks. And if you got a broken bat, the coach would say, hold on a second, I think I heard something funny, and they take your bat and tap it on something hard, and if you heard it rattle, then the bat's broken somewhere in there. But it still was together like a bat, If you see a broken bat in professional baseball with big, strong people who can swing the bat really hard, it isn't like that at all. No one ever has to check to see if they've broken a bat. When a bat breaks, it flies into two pieces. People have to dodge out of the way of the part of the bat that's flying. And the reason is the collisions in pro baseball have super high forces involved. And so so even though the bat is applying this huge force to the ball in pro baseball to hit a home run or whatever, hit the ball really fast, the ball is also applying a big enough force to the bat that sometimes it just shatters the bat into 100 pieces, you know? And so just trying to wrap your head around that, that's kind of, I think, a way to sort of think about it. Another way to think about it is like, imagine being barefoot and just gently kicking a soccer ball, you know? Like, okay, that's a reasonably pleasant idea. Now imagine stepping back 10 feet and running up and kicking it as hard as you can. You know it's going to hurt your foot, you know? Even though your foot is the winner in that collision, that ball is applying enough force to your foot that it stings your skin, you know? And so this is just something you're going to have to get used to. But those are a couple of examples, I think, of how it sort of works. Anybody have any questions right now about that, Newton's third law? Yes?
Is mass the only factor that changes?
Well, it's either, if the things are isolated and they're not being contacted with by other things, then mass is the only thing that matters. But if other things are in contact with it, then you have some sort of complicated interactions going on, you know? Yes?
So like what makes it if we have like something same mass, but they're just like going at different speeds? Like if
Mhm.
something's going faster,
Yeah.
that would be like the winner, right?
Well, yeah, that's a good question. So imagine, so let's get like friction and everything out of there. So like imagine two ice skaters skating towards each other. That sounds like a great game. Like just see how fast you can smash into each other. But all that matters is so they're going to apply a force to each other. And then Newton's second law says that force determines what their acceleration is going to be. It doesn't say anything about the speed, you know, it just says how that speed is changing. So if they both skated towards each other, they would collide and they have the same mass. They would both accelerate to a stop, you know, and their accelerations would be the same. If one person was standing there and one person was skating fast and collided with them, they would both go in this direction, you know, but they both would have the same acceleration because that force is the same. So this person would go from 0 to some velocity that way. This person would go from a big velocity this way to a small velocity this way, but their accelerations would be the same.
So Newton's third law is almost like that, just a little snippet of when they're actually like colliding.
Yeah, exactly. That's all it is. And you know, sometimes these collisions can be really short duration, like a ball hitting a bat. Sometimes it can be a long duration, like two carts that are just in contact as they roll down a ramp or something. Any other questions right now? Okay, so what this says is that a lot of times you can figure out the force on one object by another object without actually isolating the object you want. So I'm going to show you an example of that. So let's say we have a horizontal surface. And we have 3 carts. And a force this way of 20 newtons. And let's say this is 5 kilograms, 8 kilograms, 2 kilograms. And let's say we want to calculate the force on the 8 by the 2. Okay, so this is a collection of bodies with the same acceleration. So the first thing we're going to do is isolate the whole system to calculate the acceleration, and then we'll isolate an individual body. Okay? So free body diagram of the whole system. There's a weight force down. The total mass is 15, so this is 147.15. There's a pushing force from the ground onto the wheels. I'll call that N total. And then there's a 20 Newton force here. Newton's second law says 0, negative 147.15 plus 0 N total plus negative 20, 0 is equal to the mass times the acceleration. Is this system free to move along the X or Y direction? X, so I'm going to call this A0. And so the X equation says negative 20 is equal to 15A. So A is equal to negative 1.3 repeating meters per second squared. Okay, and then plug that into the acceleration vector, and you get that each one of these things has an acceleration of negative 1.3 repeating 0. Okay, and now I'm going to isolate another body. Well, we're asked for a force on the 8 kilogram, right? So your first thought here would be, let's isolate the 8 kilogram, okay? But look what happens if we do that. We have a weight of 78.48 and a normal force of N8. And then we have this force that's the one we want. I'll call that R2. And then we have this force R1 over here. Okay. This is the force, the one we want. That's the force on the 8 by the 2 kilogram. Okay. But we can't solve this isolating it this way because we have this second horizontal force that we don't know. So this Newton's second law would give one equation for 2 variables. And so we can't solve it. Okay, so what am I going to do instead? Instead, I'm going to isolate the 2 kilogram cart. Okay, I'm going to calculate the force vector on the 2 by the 8. And then I'm going to use Newton's third law. Okay. So instead, I'm going to draw a free body diagram of the 2 kilogram. There's a weight force down of 19.62. A pushing force up, I'll call that N2. There's the given force of 20. And then there's this force here that I'll call R. And Newton's second law says R0 plus 0, negative 19.62 plus 0 N2 plus negative 20, 0 is equal to the mass times the acceleration that we figured out, negative 1.3 repeating 0. And now the x equation says R minus 20 is equal to negative 2.6 repeating. And so R is equal to 17.3 repeating. Okay, so this that I circle here is the force on the 2 by the 8. Okay, so if I plug this in, we get that the force on the 2 by the 8 is equal to 17.3 repeating 0. That's not what the problem asked for, though. The problem asked for the force on the 8 by the 2. So now, by Newton's third law, the force on the 8 by the 2 is just negative, negative 1 times this vector. Or in other words, negative 17.3 repeating 0. Any questions about that? So you can use this in any case, under any circumstances. If you have two bodies in contact, and you know the force, call them bodies A and B, say, and you know the force on A by B, just multiply that by negative 1, and that's the force on B by A. It always works. That's Newton's third law. Okay, we'll do a little more intuitive stuff with it in a lab exercise, I think next week. But this is how you do it mathematically. Okay, any questions? All right, let's do the quiz.